Excited to be here. I have a background in physics myself, and I'm collaborating with physicists in University of Amsterdam, like Gianfranco Bertoni, on actually modeling detections in LHC. So I'm very excited about that. So today I'll be talking about something entirely different. I'll be talking about a technique called recurrent inference machine. That's basically a deep learning technique for doing inference in a graphical model. And I'm going to apply that to two exciting topics. One of them is sort of astronomy, so trying to reconstruct radio images of the sky from sort of these measurements, like these collections of antennas called a square kilometer array, which hasn't been built yet, but is going to be built, and LOFAR. And also to MRI imaging. And it turns out these two are extremely related, these two problems, and I'll show you some results for both of these. Actually, one correction is that I'm no longer at the faculty of UCI, but I'm at Qualcomm now, half my time. The other half is University of Amsterdam. Okay, so here's the overview of my talk. So I'll be first connecting what I will do to a new exciting development in machine learning called meta-learning. And if you were yesterday at the workshop, no, not a workshop, the symposium on meta-learning, you'll see some of the pictures copied. And then I'll connect that to recurrent inference machine as an instance of a meta-learning algorithm, but applied to inference instead of learning. And then I'll show you some results on applying that framework to radio astronomy and MRI, and then I'll conclude. But first, motivation. So why am I so excited to work on this problem, and especially the MRI problem? And that's because in the Netherlands there's a new machine that's being built, and there's already a beta version in hospitals. And in these machines you can both image and radiate at the same time. So what's wrong with just radiating? Well, you need to figure out where the tumor is, and then you're being put, you're being asked to lay very still, and then they start radiating. But clearly when you're breathing, right, you're breathing and sort of this radiation hits the wrong tissue, doing a lot of damage, or if you're very conservative, it doesn't actually eradicate the whole tumor. So this is a real problem. And so they built this machine where you can both radiate and image real time. So you basically track. So now the situation is as you breathe, sort of you track with your beam with where the tumor is. So that's a real, I think, very significant advance if this is going to work. Okay, so that basically means we have to do MRI. We have to speed up MRI imaging. That's the point here. So now I'm going to give you two sort of semi-recent papers in the community that I thought were very exciting and that were sort of co-developed with our method. But these papers have gotten a lot of attention, and I think it's very nice to relate it to this, and they're very related. So the first one has a beautiful title, Learning to Learn by Gradient Descent by Gradient Descent, and you really have to wrap your brain a little bit around what that means. But the idea is that there is some kind of learning algorithm. Let's say you have stochastic gradient descent here. And as everything designed by humans, it's suboptimal, right? I mean, this is the theme of deep learning. We can think about features, but hand-designed features are just not as good as learned features, right? And so the same thing goes for learning and inference. We can think hard about learning algorithms and updates. We can come up with cool learning algorithms. But they're suboptimal, right? And so it's much better to learn, how to do your updates. And that's exactly what this sort of method is all about. So here is the algorithm that's doing updates, right? And so here's the function, and here's the parameter that's being updated, and it receives information from a sort of a teacher that tells the optimizer precisely what updates to do. But of course, how do you then get this? This is actually an RNN neural network, which has sort of this magic box here, which produces these updates. And it takes in information, the gradient information, because that clearly is important, because gradient descent sort of depends on it. So it takes in that information, it takes the previous state, it takes a memory state. You can feed in a whole lot of information, right? And you can learn it to do the right update. But then how do you train this? Well, you have to train it on, basically looking at a lot of optimization problems or learning problems. So you feed it a lot of learning problems, and then you have it figure out how to best optimize. And here's another paper that's quite related, but applied to a different problem, one-shot learning. So in one-shot learning, you get a whole collection of problems, or small learning problems, where you get like 5 images with a bunch of labels, and you get to sort of predict the label of the images that are coming after. And so that's your learning problem. And then the meta-learning problem is you feed this whole collection of small little learning problems in order to figure out how to best learn quickly this model that does this prediction. And again, it's a very similar architecture. You start with an initial state. You send gradients and states to this meta-learner that produces an update for your parameter for this little learning problem. You feed the next data point, and you go through this, and in the end you have a learning algorithm that can then make predictions on sort of the extra sort of images that are given here that you need to label. And there was a beautiful blog by Chelsea Finn who basically connected a whole lot of problems in our community to meta-learning, and I really recommend reading that. Okay, so what is the recipe in all of these algorithms, right? Actually, Peter Abil also talked about meta-learning in his invited talk, right? So that's in reinforcement learning. So the recipe is you study some classical iterative optimization or inference algorithm. You just look at, okay, how does that algorithm operate, right? Hand-designed, human-designed. And then you look at the computation tree. You basically say, okay, this is a whole collection of updates and certain outputs of one step or inputs to the next step, and so you have some sort of computation tree. And you unroll that, and you unroll it for a fixed number of steps, let's say t steps. And you call that layers in a neural net. And then you generalize, you look at these updates and you think, okay, let's make them more general. Let's inject parameters in that update. Let's just abstract the updates away from what they look like if designed by a human. Right? And then you create targets at the last layer. This is not always trivial, but you have to go to some meta level to create sort of a supervised learning algorithm where there's targets. And I'll show in the MRI case this is really quite easy. And then you backpropagate through this network of sort of layers in order to fit the parameters of this meta network. Right? And then once you have it, you execute it on a new problem. Okay, so that's the recipe that all these algorithms follow. And we're going to apply this to inference. Now, inference and learning are not exactly the same thing. Unless you're Bayesian, then they're sort of the same thing. But in inference, we basically look at a graphical model. So that there's latent variables in this graphical model. Here there's A, B, C. These are the latent variables. And inference, if you do belief propagation or if you do some kind of mean field updates, again, that is a sequence of operations that you can unroll into some computation tree, right? And so, here you can think about message passing. A sends a message to B, B sends to A. So you can sort of think of sort of messages being sent in this graph, and there's been previous work on this as well. So here's this picture came from this paper. And you can say, well, let's stop at t iterations and just look at the updates. Let's parameterize those updates and do backpropagation. Find targets by looking at a lot of these inference problems and solving them maybe exactly, but it's expensive, but you can do it. And then backpropagate. And that's actually relating to something that we call graph convolutions. There was a beautiful tutorial on geometric machine learning or geometric deep learning or something like that by Johan Brunat and his co-authors on graph convolutions. And so basically you can think of graph convolutions as exactly that. So you basically, wrong button. Okay, so you think of it as basically a graph. Every node is sort of so maybe sort of a variable in your sort of mean field update, in your mean field problem or your sort of graphical model, and you want to do a sort of a message passing. So every neighbor sends a message, right? So it could be a belief propagation message. You update it, you push it through a nonlinearity, and you iterate. And you can then generalize that. You can say, well, let's not stick to the belief propagation or mean field updates. Just put some. Here's a state. Then here's a vector W of a matrix W, sum them up, normalize them, do a self-interaction, push them through a nonlinearity, and iterate. And then you're going to try to learn these weights. You can put that sort of in a network. You can do backpropagation on that network. It looks like this. So there's a bunch of nodes. Every node receives input from its neighbors. You push it through a nonlinearity, and you repeat. So these are the layers of computation, and then in the end, you'll have some good approximation to the posterior distribution of a variable given clamped data or something like that. And then, so this is very preliminary work. It's actually sort of like more an illustration of what we can do rather than a real result. But you could do this, for instance, on segmentation of airways of the lungs. This work with these folks here. And basically, you have on an image, you look at where possible, airways could be. You create all these features everywhere, and then you try to connect them in a graph, and then you figure out, you learn how to create a tree, an airway tree, out of all of those measurements by basically looking at a lot of pre-segmented airway examples. Okay, so then to the main sort of topic. So this is now applying this to inverse modeling. And so in inverse modeling, you start with, let's say, some object, let's say an image, and you have you basically know what the forward model is. So the forward model in this case would be downsample the image and maybe add noise or something like that. But in the case of an MRI, it would be, you have an image, and then there's the measurement process, which is you take Fourier measurements, a limited set of Fourier measurements, and maybe add noise, and those are going to be your measurements. Right? And you're interested in the backward pass, which is you're given these sparse measurements, how do I reconstruct the original image? All right, so the forward pass is given, and you're interested in the backward pass. But the problem is you typically don't have enough measurements in the, here to really fully one-to-one reconstruct the image. And this is a well-known problem in compressed sensing, and under certain conditions you can actually do very well. But typically, I view this as a learning problem. You need to learn something about the domain. So if I know that I'm trying to reconstruct an MNIST image, I can learn a model of MNIST images, and then basically try to reconstruct, basically fill in the gaps using the fact that I know how MNIST images work. And so here, sort of, I'm going to follow this recipe that I just laid out. So the recipe is, I'm going to write down the usual approach to this. So the usual approach is, I have an observation model. So X times some matrix A, typically plus noise, could be it's a well-known forward model. So that's that. And then there is a prior over X, which basically encodes how likely is a particular reconstruction given the domain. And now, okay, the typical ways, I need to find the most likely explanation X, which basically means I need to maximize this over X, right? And so now what we do is we compute the gradient with respect to X of this expression, and then we do gradient ascent on that cost function. And that works, right? But the recipe would be to look at this and then generalize, right? So let's first look at it from the point of view of a sort of a picture. So we have the prior, we compute a gradient, we have the likelihood with an observation, y, we compute the gradient, and then we add them up with the step size, which will give us a new update x, and then we feed that back into the prior and the likelihood term, and we iterate that process. Now the advantage of this is sort of the usual paradigm in graphical models, right? And people like it a lot that the computation of the prior is separated from the likelihood, and so you can train one model of images and then you can apply it everywhere to every new problem, because perhaps the domain doesn't change, but maybe the noise process changes, and so people like that. The only problem is that the optimization is actually highly, sort of entangled with the model. So certain models are easier to optimize, and a simple model that's maybe not so realistic but easy to optimize might give you a lot better results than a really complicated, messy model that's more realistic, that's impossible to optimize, right? And so these things are not independent, they're entangled with each other. And so maybe it's not such a good idea to separate them after all. Okay, so now I'm switching, unfortunately, eta to x to eta. So x equals eta in this talk, but this is some legacy issue with the slides. And so this was the original picture, right? To remind you, there is some computation which is adding up the gradients. There's the prior, computing a gradient, the likelihood computing a gradient, adding them up, getting a new estimate, and pushing them back sort of into these boxes so that you can do a next update. Now we're going to say, well, let's abstract this picture. So the first thing is going to say, well, this prior, let's integrate that into this box. So, I'm going to learn to optimize. And if I learn to optimize, basically that information about what the world looks like can sort of be encoded in this box. And the other thing I'm going to add is a memory state, because we're going to map this to an RNN, and it's typically useful to store some information of the past in your optimization process. So here's what we do. So now the update looks like x or eta, t plus 1 is eta, plus some function that I'm going to learn, which is my meta learner, depending on the gradient. So this information we can just compute, which is the information of the likelihood, the noise model, or the forward model. We have it, so we should not throw it away. So we have this gradient, and we give it to this optimizer. We have the current state, and we have the memory state. And then we learn we roll out this particular equation over t steps. We create targets, and we do backpropagation. So that's what that equation that looked like. It's just an ordinary RNN. So x, switching back to x here. So xt plus 1 is some function of the current state. And then this is very important. So we give it this gradient information. This is the forward model likelihood. We know the observations y, given our current estimate x, and we compute that gradient. So we can do all these things, and we give it as information at every state to the model, to the RNN. And then there is a memory state. And of course, I also have to evolve the memory state using a similar type of equation. So then it sort of looks like this. There's data y. These are Fourier coefficient. Goes to the likelihood model, compute a gradient. Our first estimate x goes in this box. I'll explain more about what this box is. Produces a new estimate x. X goes back into this forward model. So here you're sort of saying, well, if this were my image, what would my measurements look like? And do these sort of imagined measurements look like the real measurements? And if they don't, there's something wrong, right? And I need to fix it, right? So that's what this information encoded in this box is. There's also sort of a ground truth, which is what do I really like to reconstruct? Right? Do I know ground truth, perhaps? And that gives you also a signal to do backpropagation on. Right? So then we push that, the state, and then there's this hidden state that evolves, push it in the black box, and then we repeat for t steps, and then we do backpropagation on this. Quite simple. And then the box here, so it's sort of a general purpose kind of deep neural net. So you compute the gradients here from your forward likelihood model. You compute your state x, goes into some CNNs, some convolutional layers, go into a GRU unit that also takes in the previous memory state. Again, some convolutions, right, and then add it to the previous estimate x. So it's sort of like a gradient step, and then you repeat. Okay, so since these days we have nice software, you could just design these things like Lego blocks. You put them together, and then you push a button, and then it will compute gradients. Really convenient. Okay, and then there's of course the objective. So the objective says, you should try to get yourself targets that you're trying to reconstruct. Just not only trying to find yourself the observations, which could be the Fourier components or the noisy or the downsampled image, but also it's really useful to have some pairs of, let's say, degraded, badly reconstructed images and high resolution images. And for MRI, you can easily get those because you can basically take a normal MRI image, you can then downsample the Fourier components, then you get a much harder reconstruction problem, and then you can try to reconstruct the original high resolution image. So here's how that works. By the way, how am I doing with time? How many more minutes? 20 more minutes. Oh, okay, I've got more than enough time. Okay. Okay, so here's an interesting sort of example. So this is the original image. This is the downsampled image. So you always have to do something with MNIST. So here's that sort of first example on MNIST. So, and now here you see the trained a recurrent inference machine is it takes this image and is going to reconstruct an 8 out of it, iteratively, right? And this is the best reconstruction, and that's ground truth again. So you see that nicely, as it unrolls itself, it sort of zooms in on the right reconstruction, and also, it really needs, most of these iterations to do that. So it sort of slowly reconstructs that image. And then you can sort of ask the question, okay, which of these components were actually necessary? Yeah?
So in that MNIST example, the forward model was some known blur kernel or something?
Yeah, this is just downsampling. Yeah. Thank you. And so you can now ask yourself, which of these components are actually necessary in this architecture, right? And so we can leave out some of these links. So we can say, well, do we actually need to push the current state back into this optimizer, or do we not need that? And those are the blue lines. So these are 3 different forward models, which is Gaussian noise, this is binary noise, and this is Fourier components. And that basically is very bad. But you can also ask, do we really need the memory state? After all, gradient descent doesn't have a memory state, so we added this. So is this an important component? And well, truly, it does make quite a bit of a difference. So I guess these are different noise levels or something like that. So really adding all these ingredients in there does help a lot in getting high accurate reconstructions. Okay, so here's some more examples on normal images. So we have sort of a noisy and sort of a denoising problem. So this is the problem you try to denoise, and then sort of you can see it will nicely reconstruct. Here's a super resolution problem on real images. Of course, it's better than by cubic interpolation, but we did compare it to a whole lot of other methods as well, and it seems to perform quite well. So here's more super resolution results comparing to sort of other state-of-the-art methods, and you can see sort of the details are being reconstructed very nicely. I'll skip the bold numbers for you, but they are bold for REM. And then, so here's then the application to astronomy. So now we are at the physical sciences part of my talk, I guess. So the problem of reconstructing radio images of the sky is as follows, and this is a really exciting project where they are planning to build thousands of, they were building thousands of antennas distributed in Australia and South Africa. And all of these antennas together sort of form one massive sort of antenna by correlating all the measurements, right? And basically every pair of antennas forms the basis of a measurement of a Fourier coefficient, where the coefficient frequency depends on the distance, and the orientation clearly depends on the orientation of the original 2 antennas. So you have an image of the sky here. That's, let's say, the ground truth image of the sky. So let's Fourier transform that image. Then sort of this is what that would look like in the Fourier domain. And then the process of subsampling using this array of antennas really looks like this. It's a bit hard to see. But basically there is a subset of these Fourier measurements are actually measured. And because the Earth is rotating, you see these sort of circular patterns in there. And then sort of the easiest thing you could try is to say, well, let's take this subsampled set of Fourier components and do an inverse Fourier transform. Because if we had this, we would have gotten the right image. But unfortunately, it looks like really bad. So there's just not enough information there to actually get this reconstruction well. And of course, things like compressed tensing do improve on this. But none of these methods actually learns, right? So they basically start over again, and if you think of them as Bayesian methods, they're extremely elementary because they sort of say, well, there's a prior that basically says that the measurement should be sparse. But there's a lot to learn, right? You can just look at a lot of images and learn things about, what do radio images really look like? And then you can try to use that statistics in order to do the reconstruction for you. So that's what we set out to do, which is, we know this forward model very well. We know how to get from here to here very precisely, right? So now we want to train a model that goes backward using deep learning. So we had sort of Joran Peters work on this for his master's thesis, did an awesome job. So basically, again, so we have the image of the sky. These are really pretty images, and then you have these Fourier measurements, typically sparse. And then you have to you downsample these and then try to reconstruct that. Okay, so here's some results. There's a bunch of other tricks you have to really do to make this work, so it's but I'm skimming over those. So here's the clean image, and then here's what we call the dirty image, which is basically the inverse Fourier transform of the sort of the subsampled image. So that's really bad. And then sort of here is what we, after, so this is a baseline RNN, and this is basically our best version of it that needs to reconstruct this. And here's a bunch of results and this is actually the best competitor, I think, maximum entropy method. And you see here it's pretty good. So in fact, here basically these two were somewhat similar. But for other examples, it totally fails, and our method does quite a bit better than MEM. Okay, so here you see the RIM, which is the recurrent inference machines, our method, as it sort of unfolds its inference over time. So this one is pretty easy. It's more like a point mass. Well, okay, it sort of doesn't reconstruct that, but you see it sort of does it over time, and the error actually does get smaller and smaller. And here's another example where it needs more time to actually find a good estimate. And again, you see that the error gets smaller and smaller as it proceeds over time. Okay, and then the last application is for MRI imaging. Again, it's very similar. So you take an MRI image, which is basically a bunch of Fourier measurements. And given the Fourier measurements, which are subsampled, so I'm not sure if you have been unlucky enough to be in one of these machines, but you sort of hear this ding, 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 ding. And every time you hear one of these, then they're doing these Fourier measurements. It takes quite a long time, actually, to, you could easily be there for half an hour to an hour. And it's actually quite expensive, too. And so really, if you could subsample those Fourier measurements and do a good reconstruction, that would be very helpful. So here you see sort of the subsampling, what we do. So this is the original Fourier plane, and we sort of having different versions of subsampling. So this is like up to 6 times downsampling of the Fourier measurements, 4 times downsampling, and 2 times downsampling. And sort of this is the clean image, a patch of a clean image, which is a target, and this is the sort of initial estimate based on a subsampled image. Okay, so here are the learning curves. We have actually 2 implementations, and the reason is that this is actually a complex problem, in the sense of with imaginary numbers, and so you have to work with imaginary numbers, and so you can try to be very sophisticated about it, which we wanted to do, and so we did Vertigan calculus, and we felt very good about ourselves that we figured this out. Unfortunately, if you just take 2 real planes, it works just as well or even better, so we had to sort of toss that out the window. But so here I'll show 2 of these curves that basically do equally well. So these are the training curves, and here are the sort of test curves. And then here is a little video of going through the slices of the brain, right? And this is ground truth, and this is a reconstruction, and this is the original image if you would do the ordinary method. And you can sort of see that it really gets, the target quite well. And then here you see as it progresses over time. So this is the REM in steps, trying to reconstruct the original image. Here you have the error. This is the target, and this is as it sort of re-estimates to the target, right? So it really needs the steps in order to kill the error here on the right-hand side to do that. So here we look at the number of training steps. So here this is as we are training the model, and this is the number of time steps in the RNM. So you start here, this is the first reconstruction, second reconstruction, up to the 10th time step in the reconstruction. And the error is like low down here and high up here, yellow, right? But you can see that, in the beginning it's basically not doing very well, and then as it's starting to train better and better models, it will improve its reconstructions basically over time, and also earlier in time with less steps. Here's some further results. They're a bit hard to see, I think, because of the resolution. So we compare to some competitor algorithms like compressed sensing algorithm that's out there. And so this is 6 times downsampling, 4 times downsampling here. Yeah, RAM, target, and compressed sensing. So some sort of numerical results. These are 2 measures. This is the error measure, so low is good, and this is some similarity measure, so high is good. And these are the 2 sort of variants of our algorithm versus compressed sensing. And with small subsampling patterns, in fact, so they're doing sort of equally well. But then as the subsampling gets higher and the acceleration gets higher, our algorithm wins out over the compressed sensing algorithm. And then you can also look at standard deviation across subsampling patterns, because you can sort of sample subsampling patterns and see how stable the algorithm is if you choose a different subsampling pattern. And again, sort of the standard deviation of the results is lower, which means that it's sort of more robust to which subsampling pattern you actually pick. Okay, so I'll conclude. So I think meta-learning is a pretty exciting new area, and we've applied meta-learning here to inference, and it basically, it speaks to the fact that everything that humans design should be improvable by learning, right? So if you see anything anywhere that people have designed and you have enough data, you can probably improve it by some kind of learning procedure. So the RAM is a method that unrolls inference in particular and learns to solve inference problems. It's connected to a lot of work that I really didn't go into very much, but there's work in computer vision that connects to this, and all sorts of other good stuff. And it has great potential to improve both speed up and accuracy in radio astronomy and MRI image reconstruction, in my opinion. And in particular, I'm very hopeful that, in fact, one day we can actually do real-time MRI imaging to build these kinds of machines, or to make sure that we can radiate and image at the same time. Thank you very much.
Thank you very much for the great talk. So unfortunately, we don't have extra microphones for you to ask questions. So if you have any questions, we do have time. Please be as loud as possible. The room is relatively small, and if the speakers want to repeat or summarize the questions, that'd be great. Maybe did you have your hand up? Okay, great. Go ahead.
So I didn't get a sense of how many images, for example, if you want to give examples you used to train this thing, do the training step. And then I have a following question.
Yeah, so it's in the hundreds, let's say.
Okay, so it's fairly small.
Yeah, fairly small. But there's a lot of sharing, actually, because these are convolutional architectures, and so, it's basically the statistics, from one side of the brain to the other side of the brain might not change all that much.
So my question is, given that you have a certain training sample and then they have some distribution of fundamental, things that are inside of there, how can you make sure that, for example, for radio astronomy, you may have a variety of type of objects that you imagine that you have in the training sample? How could you make it? Are you sure that you're not hallucinating something that you saw from the training sample?
Yeah, that's a great question. That's of course, but I think that's fundamental to, it's a much bigger question. It's to modeling in general, right? So it has to do with the fact if you put your inductive biases in a model, you're bound to bias your results to seeing the things that you put in there, right? And so the game is, if you have a lot of data, you can make your models very flexible and not miss out on things. But if you don't, you have to live with the fact that you're biasing towards things that, that you're put into the model, right? And so there's still a game in science that is like hypothesize things and then try to find them. It's not a magic bullet that will basically just, you just push the button and it will just discover everything for you. So anyway, so I think it's a very good point, but there is some trade-off, and we sort of have to live with the trade-off, I think.
We have a question over here.
Do you have any suggestion on how you extend it if you don't have access to the gradient of the local white effect?
That's a really good, interesting question. I haven't thought about it, but maybe relax. Oh, sorry, yeah. So the question is, what if you don't have gradient information? And I would say relax. And you can understand. So relax is a new method, or rebar, where you basically do surrogate modeling. So you have a model that tries to imitate the forward model. That's expensive, but at the same time you can then compute the gradients of that model and sort of try to sort of negotiate those two things. But that's a great problem to look at. Yeah.
Question right behind.
Yeah.
So is there a way to do this without RNNs, like in model agnostic meta learning?
Sorry, what was the last meta?
So yeah, model agnostic meta learning was figured by Justin Finn, and it doesn't use RNNs to do.
Oh, I see. So is this the model where you try to get to a good initial point from where you can learn? I think in this case, the convolutions, the iterative convolutions to me seem extremely important to analyze these images. So it seems very hard to get rid of that part. So maybe there is an interpretation of this which would say something like, you would move towards a particular state that from where you can do a little bit of extra learning. But the convolutions seem to be totally, the most important part of this. So I wouldn't want to get rid of that. I see this guy's setting up his hand for a very long time.
Kind of going back to the first question in some ways. So you started with a model that was a very explicit probabilistic model. You had p theta of x in your prior. And by moving to this neural network architecture, you've essentially obscured that, right? You've made it very implicit.
Yeah.
And so I'm wondering whether that leads to problems where, because an advantage of that explicit p theta x is that it lets you really kind of control your inductive bias by talking about what it was. So for instance, like in neural network-based super resolution, hallucination of details is a real problem, right? These things are very, very crisp, but they'll hallucinate things that aren't there. And I'm wondering how you would think about those trade-offs.
That's also an interesting question. So it's true that we sort of gotten rid of the prior and we became very implicit in the RNN. But if you have a really good model for your prior, you might actually just put it in there, right? You just take your prior, take the gradient, and also feed it into your RNN, right? And so that's something that could potentially work really well. So we haven't tried that, but you can negotiate how much prior information you want to stick into that RNN architecture, or how much you want to just. But the downside, of course, is if you put a prior, and the prior isn't really, your imagination wasn't good enough to figure out what the real world looks like, which is often the case. Then, of course, you might actually bias yourself in a direction that you might not want to do.
And I guess as one slight follow-up, in the work you showed, certainly the reconstructions you're making were pretty blurry compared to the original ground truth, and that kind of protects you from hallucinating details in some ways, right? You're not trying to reconstruct something that's as sharp as the original.
Actually, we would like to reconstruct something that is as sharp.
Then you're more likely to hallucinate, probably. Right?
Yeah, you might. So you might sort of edit out certain structures, and I guess that's what you would have to sort of take into consideration, that it is a reconstruction, it is a real image. But in the end, you could argue that it's sort of misleading because it looks like so real, so it must be real, and so that might not be the right thing. And the other thing is kind of pleasing to look at, so it's a trade-off, I guess.
Thank you.
Perhaps one last question here.
I'm just curious, have you thought about, in the MRI example, when you're trying to kind of do fewer of these in the subsampling, have you tried to include something like that in the actual optimization, so your choice of how you collect the data and the active learning sort of plays?
Right, so that's so the question is, can you also optimize over which Fourier components to actually measure? So that's experimental design, and in fact, in the astronomy application, people do have these mobile sort of antennas that they can move into position, and then you can start optimizing over that as well. That's a super interesting problem, but we haven't detected. But that's, of course, now it makes a lot of sense to start optimizing over what is the optimal subsampling design. And one thing that we did notice, but again, this is by looking at the results, is that you really need to maintain your low frequencies. Those are super important, and you can subsample the higher frequencies because those are easy to fill in, I guess, using the method. But that's a very interesting research direction.
Okay, let's thank our speaker one more time.